All right, guys, can you hear me? Can you hear me? Can you hear me? Okay, let me see your faces. Let me see your faces. I only had 25 in my last class. I was pissed. I was pissed. I want 35. I want 35. Okay, stand up, wherever you're at, stand up. Stretch, stretch. Oh. All right, let's sit back down. Let's sit back down. I'm hoping everybody had a good Tuesday. What did we introduce last time in class? What did we introduce? The dot product, okay? We had our scalar product and we had our vector addition. And then we kind of knew how to do those a little bit. Some information. You have a WebAssign that's due when? You have a WebAssign that's due when? Friday. So we have our WebAssign that's due Friday. Also, Quest number one. Quest number one is going to be next Wednesday. And it's going to be on 12-1, 12-2, and 12-3. It'll be on 12-1, 12-1, 2, and 12-3. You can expect at least one proof. Likely related to having to prove one of these properties. 1, 2, 3, 4. And there's going to be a fun one that's going to come along today that's going to be property 5. You can expect some homework, stuff like the homework. It's going to be about 50% WebAssign. You'll take it in class, you'll have half the class to take it. 50% WebAssign, and then 50% will be a PDF handwritten copy that I send to you. If you can print it, that's awesome. Okay? If you can't print it, just work on regular white paper. And then you're going to take your phone and use your scanning app on your phone to create a PDF scan of it and then upload it to Canvas. But I'll talk more about the logistics, okay? But I want you to be thinking, what do we have next Wednesday? Quest 1. What's due this Friday? WebAssign. Okay, so we're just leaving. Why, Dr. Warren, why do we have a WebAssign due on Friday? Because I don't want you to be screwing up with the WebAssign on Wednesday. Okay? I want you to know how to put in your vectors. I want you to know how to do all that stuff. So by having 2 of them due immediately, I'm hoping that will help you out when you head into your first quest. Okay, now, last time we derived a very important formula for any triangle. I've got a triangle whose one side is A, whose other side is B, and whose other side is length C. I've got a triangle whose one side is length A, another side is length B, and whose other side is length C. Look at that triangle. Is that a right triangle? And you're like, hell no, it doesn't look like a right triangle. But let's imagine that I know the angle theta here. So I know that this is A, this is B, they give me this angle, and my job is to cut a piece of wood, that length there, that length C. Without looking at your notes, write down the formula from the Greeks that would help you do that. Without looking at your notes, write down the formula from the Greeks that would help you do that. I don't want you to ever forget this formula. Okay, wherever you're at right now, hold it up so I can see it. Hold it up. Some of you aren't holding up anything. Whatever you got. I don't care if you got nothing. Hold it up to the screen. Now I'm moving up to the front so that I can see what you've got here. Some of you are right. Okay, so you help me out. What is the formula? What is the law of cosines? C squared would be equal to, C squared would be equal to A squared plus B squared. You're like, hey, Dr. Warren, it's the Pythagorean theorem. No, it's not. It's not. There's this punishment term because we don't have a right angle. That punishment term is it's a minus 2AB times the cosine of theta. Okay, that's one thing we derived last time. The other thing that we derived was the length of a vector. How do you find the length of the vector? How do you find the length of, if I have a vector, let's just say it's the vector A. I've got the vector A. What expression represents how long? What expression represents how long that vector is? How long is the distance from here to here? What expression represents how long that is? I'll keep asking. Maybe if I ask it like this. What expression, boys and girls, represents the length from here to here?
The norm of A.
The norm of A. Gordon, was that you, man?
Yeah, that was me.
Okay, awesome. The norm of A. So the norm of A represents that distance. Now, without looking at your notes, flashcard for Wednesday. Flashcard for Wednesday. How do you find the norm of A? What's it equal to? What's your flashcard? How do you find that? I can tell none of you are ready. Stuart. You're like, damn it, Dr. Warren, don't ask me. Stuart, how do you find the norm of A?
The square root of A1 squared plus A2 squared plus A3 squared.
Perfect. The square root of A1 squared plus A2 squared plus A3 squared. Okay, so here's some formulas for our dot product. Here's some formulas for our dot product. These are all pretty much flashcards. The definition of A dot B. The definition of A dot B. Now I'm going to see if you guys can actually read this or not, because I'm not sure exactly how blurry it is. A dot B by definition is equal to A1 times B1,
A2 times B2,
A2 times B2,
A3 times B3.
and what do we do with those three things? What do we do with those things? We
Add them.
together. We add them together. So it's A1 times B1 plus A2 times B2 plus A3 times B3. If I give you two vectors, is that really that hard to calculate? If I give you two vectors, is that really that hard to calculate? You're like, no, to give me a calculator, Dr. Warren, it's not bad. You just multiply the components together and add them up. Now, this could be something you might have to prove on Wednesday. That the scalar alpha times A dot B gives you a scalar. Because this is a scalar and this is a scalar. And a scalar times a scalar is a scalar. You get the same scalar if you do alpha times A first, distribute this across there, and then dot it with B, and you get the same thing there. The proofs would always start like this. You'd be given A and B are elements of the vector space, and alpha is a real number. It's a scalar. Your next move would always be, then A is equal to A1, A2, A3. B is equal to B1, B2, B3, where A1, A2, A3, B1, B2, B3 are elements of the real numbers. What would be your justification in a proof for that? What would be your justification? Why must these three numbers exist so that these ordered triples would be there? What would be your justification as you're getting ready for next Wednesday?
Definition of the vector.
By the definition of a vector. By definition of V. By definition of V. And then the next thing you would do is you would just set up this. You would say, well, given alpha times A dot B, your next move is going to be, this is given. The justification in the argument, it's given to you. This would be equal to alpha times A1, A2, A3, the component form, the ordered triple form, dotted with B1, B2, B3. And this would be by substitution. And it's really substitution on V. It's really substitution on V. Now, how many people are pretty comfortable? How many people are pretty comfortable they can do that dot product? Then you're going to use the definition of the dot product. Then you're going to bring in the scalar alpha. And then you're going to start working backwards to where you can start pulling that out. You're going to be making a proof like this next Wednesday. You're going to be making a proof like this. Math is proof. Math is proof. If you don't like proofs, don't be a math major. Don't be a math major. If you don't like proofs, don't be a math major. I have a lot of kids, they're in 245, and they're like, Dr. Warren, I hate 245. I just hate math 245. It's nothing but proof. When does proofs end? And I'm like, the kid's name was John. I'm like, John, man, you got the wrong major. You got the wrong major. This is what math is. What's the prefix on 237? What's the prefix on 237? It's called Math 237. Guess what there's going to be in this class? Just guess. Guess what there's going to be in this class? Don't say it, Dr. Warren. Proofs. Do you hear me? Deep, dark, sinister. Proofs. You have a quest when? You have a quest when?
That's it.
Okay. Okay, give me a vector. Give me a vector. Give me a vector. I won't do it now. I'll freeze, like I'm just frozen.
2, 4, 8.
I heard the 2, the 4, and the 8. Okay. Give me another vector. Give me another vector.
1, 3, 5.
1, 3, 5. You know what's really sad? You know what's really sad? Is you guys are so much more creative than my first class. You're so much, I was like, give them a vector. You know what they gave me here? 1, 2, 3. And I'm like, okay, out of all the real numbers you could have picked, you picked the numbers 1, 2, 3. I mean, at least you did. Can you read that?
2, 4, 8.
Josh, can you read that? Josh.
Is it 248?
It is 248. It's 248. Just want to make sure. Guys, I'm still trying to get a feeler for how much you can see and how much you can't see. I kind of feel like I'm teaching Helen Keller. You know, that's kind of what I feel like. I'm wondering, like, sorry, that's probably not politically correct. Okay, but I feel like I'm teaching Helen Keller. You know, like I'm like out there trying to hold up Braille. Okay, I gotta stop. Okay. So imagine that I plotted these vectors. Imagine that I plotted these vectors in three-dimensional space. How would you plot this one? What would you do? You've got your, now guys, this is not going to look real good because of this wide angle lens. Okay. I mean, but I've got my three-dimensional space here, okay? But you would go out to over 4, and then up 8, and then we would go, for the second one, we'd go out 1. Now you guys pick these, over
3.
and then up 5. So let's imagine that I've got that. I'm going to try to, let me get this out of your way. I'm just going to draw it, and you guys can draw it too. I know you're not going to do a great job, and I'm not going to do a great job. We're just trying to get a visual image. This would be which axis? This would be which axis?
X.
X. This would be which axis?
Y.
And then this one?
Z.
Z. So now I'm just going to pretend I've got this vector here, which is A. Then I got this other vector, which is 1 over 3 up 5. And we'll just pretend like that's the vector B. Those are the direction vectors. Now we can kind of see these. We can kind of see these in three-dimensional space. Maybe they look something like this. Now, imagine that you were given this problem. Find the angle between these two vectors. You've got specific numbers. Find the angle between those two vectors. Might that be an important engineering problem? Could that be related to an important engineering problem? Or something in physics, if we're related to forces? So the question is, how do we do that? And you're like, Dr. Warren, that's hard. In three-dimensional space, it's hard enough in a plane. Let alone now, I've got these vectors flying out here in three-dimensional space, and you want me to find the angle between the blue vector and the green vector. And what we're going to do today is going to make this almost trivial. What we're going to do today is almost going to make this trivial. Are you ready? Are you ready? Are you ready? Stand up again, stand up again, stand up again, stand up again. Some of you aren't standing. Okay, okay, run in place, 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 run in place. Jump, 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 turn around, jump. Okay, now sit back down, sit back down. That should have got you going. We left off last time, well, these are some properties we had. The dot product is, use a big math word. If A dot B equals B dot A, then the math product is, use a big math word. Commutative. It can commute. You get the same thing if you do A dot B as you get if you do B dot A. Same scalar. It's also A dot B plus C, or minus, is equal to A dot B plus A dot C. So it's also, use another big math word. Use another big math word.
Distributive.
Distributive. It's also distributive. And you're like, Dr. Warren, is it associative? Well, then A dot B dot C would have to be equal to A dot, don't write any of this down, it's just complete crap. You're like, well, Dr. Warren, that looks cool, but this is just garbage. This is complete, okay? This is complete crap, because a vector dotted with a vector is a vector dotted with a vector is a vector dotted with a vector is a scalar. You don't dot product scalars. You don't dot product scalars. So this is just complete crap. This is just complete crap. So it's not associative. And this was the last result, and this is kind of a fun one, is that A dot A is equal to, I just put it in a box, A dot A is equal to the norm of A squared, the norm of A squared. Okay, this is going to be so much fun because you're geeks. This is going to be so much fun because you're geeks. We're going to derive a super cool theorem using our geometric algebra. We're going to derive a super cool theorem using our geometric algebra. I've got our two vectors, and I'm probably going to just pretend like they're over here. Imagine that I've got this vector B. I'm not even going to worry so much about these vectors. We'll come back to them. I've got this vector B here, and I've got this vector A there. This is the vector. I hit, you hit. Vector. This is the vector A. At your seats, draw the vector B minus A. At your seats, draw the vector B minus A. Because you've got to imagine you'll be doing this next Wednesday too. And guys, the direction does matter. You're like, I got most of it right. Okay, if this is physics, and you got the wrong direction, I'm pissed. I'm pissed. You're pushing me into the black hole. Okay, hold up to the screen what you have. Hold up with the screen. You should almost be able to do this just like this. You should almost be able to do this just like this. Hold up to the screen what you got. Hold up to the screen what you got. I'm now at the front of the room. I'm now at the front of the room. I'm looking. Oh, I can't see it. Some of it's so blurry. Mason. I like Masons. Okay. Mason. Okay, guys. You just do what with the two endpoints of the vectors? You just do what with the two endpoints of the vectors? Connect them. And then your question is, which direction does it go? Which direction does it go towards A or does it go towards B?
B.
It goes towards B. You're like, well, how do I know, Dr. Warren? Well, write it down. You think this is the vector B minus A. Let's use the geometric vector addition. Head to tail. Does A, put the but here, B minus A equal B with our vector addition? our geometric vector addition. Does head to tail rule, does A plus B minus A equal B? Yes or no? Does A plus B minus A equal B? And the answer is, I'm doing this, so you answer. You froze me again. What was the answer? I'm unfrozen.
Yes.
Yes.
Oh, no, good. There we go. You unfroze me. Thank you. You brought me back to life. Okay. Now, what if I did A minus B? What What would happen? What if I did A minus B? What would happen? What if I did A minus B? What would happen?
It'd just be flipped.
It would just be flipped. It would just be flipped. So let's do the algebra. I mean, just do the algebra. A plus B minus A is what? A plus B minus A is what? Just do the algebra. What do you get? A plus B minus A is what?
B.
B. So that tells you, that gives you, you don't need to screw it up. You don't need to mess it up. The head always points to this guy. The head always points to that guy. Okay. What shape have you just created? What shape have you just created? Look at the shape you just created. What do you have?
Triangle.
Triangle. Now let's call the angle between these two vectors theta, because that was the question. Is there a way to find theta? Is there a way to find theta? Now look at this, and let me get out of the way, and look at this. Look at this, and look at this. Do they look similar? Do they look similar? Yeah, but this is a length. This A is different than this A. This is a length. The law of cosines is a length. What represents the length of this vector? What represents the length of this vector?
The norm.
The norm. So the length of this vector would be the norm of A. You guys fill in the other lengths. You guys fill in expressions that would represent the other lengths. Okay, so over here, what do you guys have here? What do you have there? What do you have there? What do you have written down? Anyone? What do you have? What do you have? What do you have?
The norm of B minus A.
Norm of B minus A. Okay. Now, think true or false. Does the norm of the ice cream cone vector plus the smiley face vector equal the norm of the ice cream cone vector plus the norm of the smiley face vector? What do you think? What do you think? Does that true? Is that true or false? Say that.
Hell no.
I mean, what is it that makes us want to distribute everything? I think it's the devil. I think the devil just gets in your ears. When you don't know what to do, you immediately think, oh, let's distribute. But you're always wrong. You're always wrong, but you still do it. It's like alcohol. I mean, guys, yes, 2 times 5 plus 7, distribute away. A dot, B plus C, please distribute away. Sine of theta plus psi. No, it's not sine of theta plus sine of psi. E to the x plus y is not e to the x plus e to the y. Whenever you have that desire to distribute, cause yourself pain. When you say, I want to distribute, don't do it, man, don't do it. I want to distribute, don't do it. Okay. Does the norm of ice cream cone plus smiley face equal the norm of ice cream cone plus the norm of smiley face?
No.
Okay, good. Does the norm of B minus A equal the norm of B minus the norm of A?
No.
Hell no. Okay, so we've got that. How about what represents this distance right here? What represents this distance right here?
The norm of B.
Norm of B. Okay, now let's go over to our law of cosines, which we've got right here, which we've got right there. Is this a triangle? Is this a triangle? Some of you aren't focused. Is this a triangle?
Yes.
How long is this side? How long is that side? How long is that side?
The norm of A.
And how long is this side?
The norm of B minus A.
And how long is this side?
The norm of
The norm of B. So let's use the law of cosines. We got the angle theta here. We got the angle theta here. Who's in the C position? Look at that. Look at it carefully. Who's in the C position?
the norm of B minus A.
The norm of B minus A. So what I want you to do is over here at your C's, plug in the right quantities for your law of cosines. Plug in the right quantities for our vector triangle over there in your law of cosines. And if you're watching the video right now, because I can see you over there, if you're watching the video and you didn't come to class, you better be plugging it in yourself right now. Okay, hold up what you have to the screen. Hold up what you have to the screen. Let me see what you've got. Hold up what you have to the screen. Hold up what you have to the screen. Okay, good. So what would go here, guys? What would go there? What do you have there? What do you have right there? What do you have there? I'll keep asking.
Of B minus A squared.
The norm of B minus A squared equals the
Norm of A squared.
norm of A squared plus the
Norm of B squared.
norm of B squared minus 2 times the
Norm of A.
Norm of A.
norm of A times the norm of B. And then times the, what's at the end? What's at the tail? What's the caboose? Cosine of theta. Now I'm willing to bet if I'd given you guys some time and just said, okay, put these in here, try to come up with some relationship for theta, I'm almost willing to bet everybody, okay, I'm lying. Some of you might have, with a half hour, gotten to this point. I think at this point, you would have gotten to this point. It's this next move I don't think you would get. I wouldn't have gotten it. I'm not smart, guys. I'm not smart. I had a 1.9 high school grade point average. Okay? I'm just old. Okay? When you're around for 60 years, you pick up on a few things. We know the norm of A squared, and this is the key. We know the norm of A squared is equal to
A dot A.
A dot A. So in all of these squares, forget about this. In all of the squares, replace these with the dot product version. Replace those with the dot product version. So wherever you see that norm squared, use this identity we derived last time and replace it with the dot product version. See, this is active learning. This is where I just don't write stuff down. You do. I was looking at the screen, and I'm like, who just got up and left the room? And it was me. It was me. I was the one who was walking around. Okay. So what do you have here, guys? What do you have here? What do you have there? What do you have there?
B minus A dot B minus A.
B minus A dot B minus A. And what do you guys have here? What do you have here?
A dot A.
A dot A. And what do you have here?
B dot B.
B dot B. Now, I don't want to mess with square roots. I'm going to let this guy just hang. You're not invited to the party. You can't come to the fraternity. You're just going to stay out there. You got square roots. Okay. Can we distribute with the dot product? I don't know, Dr. Warren. Are we allowed to distribute? Are we allowed to distribute with the dot product?
Yes.
So let's do that. Let's just start distributing over here. I'm going to think of this as C. I'm going to think of this as A. This is B. This is plus, but and this is C. So this would imply logically that B minus A dot B, that's distributing it to that guy, minus B minus A dot A is equal to all that stuff on the other side. Is equal to all of that stuff on the other side. So I distributed this vector to both of those, just like you did in high school, except now we're using vectors. Could I distribute again? Could I distribute again? Could you distribute again? Could you distribute this way? Could you distribute this way? And the answer is yes. So go ahead, distribute again and see what you get. Now, for sake of time, guys, you guys help me out. What do you get? What do you get here? What do you get here? What do you guys get there? If you distribute this to that and that, what do you get?
B squared and then minus AB.
We'll say B squared, but we'll just call it B dot B. Can you guys see that? Can you see that or not? Can you see down there or not? Not much. This is B dot B, then minus
Yeah.
A dot B. Now I've got to be careful with this here. Then minus
B dot A.
B dot A.
B dot A. Then minus
A dot A.
A dot A. Okay, now let's take the helicopter up out of the woods again. Like Dr. Warren, what were we trying to do again? What's the motivation for this? I feel like I'm in Vietnam. What's the motivation? I've been in the jungle too long. We're trying to find the angle between two vectors. We're trying to find a way to find the angle between two vectors. And what we did is we just put out our vectors, because that's what's given to us. We found a triangle. It wasn't hard. A, B, we do B minus A. We said this represents this length, this represents this length, this represents this length. Then we plugged it into our law of cosines. And this was really the hard part. The moment it was here, to know to go ahead and do that, you wouldn't have done. You wouldn't have known how to do that. But everything else has just been algebra. Everything else up in that has just been the algebra that we've created. Now I'm kind of jammed down here. This minus is going to hit this guy and this guy. This minus right here is going to hit this guy and this guy. So I'm now going to go up. Can you guys see here as I still try to figure out my room? Can you see up here? Can you guys see that? So I'm going to rewrite this. I would have my B dot B. And then I've got minus A dot B. Now I'm going to take this minus there, minus B dot A. And then I take this minus to this guy, but that's going to turn that into a plus A dot A. And this is everything that's on this side of the equals. This is everything that's on this side of the equals. But this is equal to this, which is equal to this. So let's put everything over here on the other side of the equals. I'm a little jammed up. I get A dot A plus B dot B, then minus 2 times the norm of A times the norm of B times the cosine of theta. Now I realize I'm talking, you're writing, you might not even be listening. So I'll let you write that down. Now look at that equation, guys. What do you see? Look at that equation. What do you see? I mean, just stare at it. You got this side is equal to that side. What do you see? What's alike on both sides? What's alike on both sides?
There's an A dot A and a B dot B on each side.
There's an A dot A, there's an A dot A here, and there's an A dot A there. Take out your sword. Take out your sword. Take out your sword. Take out your sword. Hold up your sword. Hold up your sword. Hold up your sword. Let's slash these away. Slash. Slash. Say it, say it, say it, say it. It'll help you.
Slash.
And then
Flash.
the enthusiasm. We're proving like one of the most remarkable results, and you guys are slash, slash. Your excitement should be almost overwhelming right now. Let's see what's left. I've got minus B dot A, and then I've got minus A dot B, then minus B dot A is equal to minus 2 times the norm of A times the norm of B times the cosine of theta. Is the dot product commutative?
Yeah.
Does A dot B equal B dot A? So yeah, this is the same thing. This is the same thing as A dot B. Well, how many minus A dot B's you got?
2.
2. So this is the same thing as saying minus 2 A dot B is equal to minus 2 the norm of A times the norm of B times the cosine of theta. But that would make A dot B equal to, that would make A dot B equal to the, that would make A dot B equal to
The norm of A dot the norm of times the norm of B times cosine theta.
times the cosine of theta. And this, guys, is a massive, that is a massive flashcard. That is a massive flashcard. We are going to just use that over and over and over again. Yay. Okay, stand up again. Stand up again. I know you need this. Look at anything that'll tell time. How much time do we have left? How much time do we have left? How much time do we have? How much time do we have left?
37 minutes.
37 minutes. Stretch again. You're out of shape. You're out of teaching shape. You're out of shape. I'm out of shape. Oh. Oh. Okay, sit back down. See the light. See the light. See the light. Did you see the light? Say that.
See the
No. Sorry, I should read this.
A dot B equals the norm of A times the norm of B.
Times cosine.
And now go Eureka. Say that. Eureka. Okay, now again, we had our two angles. out here in three-dimensional space. These could represent beams. These could represent beams. And now imagine that I wanted to find the angle between the blue vector and the green vector. Are we in better shape than we were before? Are we in better shape than we were before? I mean, now just look at me, guys. These were your two vectors. How many guys think they could get the dot product of these two vectors? I mean, if we were actually trying to do this, how is it that hard to find the dot product of two vectors? Now, I know, Dr. One is just 2 times 1, 3 times 4, 8 times 5, and you do what with that? You do what with those guys? Add them together. I mean, you want a calculator, but could you get the square root of A? Could you get could you get the norm of A? Could you figure out the norm of A? It'd be the square root of
2 plus 4 plus 8.
2 squared plus
Squared.
2 squared plus 4 squared plus 8 squared. The norm of B, 1 squared plus
3 squared.
3 squared plus,
5.
and you take the square root of that. And if I did that, I'm not going to do it, but if I did that, what I would have is, I would have that, if I looked at A dot B, I would have, just thinking of my vectors that I've got up here, A dot B would be equal to what number? A dot B would, for your two vectors you pick, find A dot B. And I'm hoping you're almost done now. I'm hoping next Wednesday that you'll be done almost like that with this. What scalar did you get, guys? What scalar did you get for the two vectors dot product? Anyone?
54.
Anybody else get 54? Raise your hands. Anybody else get 54? Okay, yeah, it is 54. But that would be equal to the norm of A. So find the norm of A. Find the norm of A. There's your vector A. Find the norm of A. And what do you have for that? What's the square root? What is to be the square root of what? How long is that vector A?
Square root of 84.
What is it?
84.
84?
Square root of 8.
Times the norm of B, times the norm of B. How long is B? How long is B?
Square root of 35.
Square root of 35. Times the cosine of the angle between them. Times the cosine of the angle between them. So if I have 54 divided by the square root of 84 divided by the square root of 35, that would be equal to what? If I take these guys here, that would be equal to what? Cosine theta. So if you wanted to figure out what theta is, you would do what to both sides? If you wanted to find out what theta is, you'd do what to both sides?
Inverse cosine.
Inverse cosine. You could either call it the arc cosine or cosine inverse. Now listen to me and listen good. It's in radians. It's in radians. This is an angular measure in radians, not degrees. This is an angular measure in, what did I just say?
Radians.
Please don't bring down my bridges. Please don't bring down my bridges by screwing up radians and degrees. Now I've got to ask, guys, if I gave you any two vectors, do you think you could find the angle between them? And I dare say, it's not that hard. Like, Dr. One, it's so hard. Not really. Think about it. These are any two vectors in three-dimensional space. Holy hell. And you can find the what between them?
The angle.
The angle. Just by the simple arithmetic. Just by the simple arithmetic. Does the geometric algebra seem to have some benefits? Does the geometric algebra seem to have some benefits?
Yup.
Yeah, and we really don't have any idea just how much yet. Okay, so stand up again. I know, but it's been an hour. You're not in shape. You're going to need it. You need a visual break. How many of you guys are in the same place all day long to go to your classes? I'm so sorry. I'm so sorry. Josh, you're not standing unless you got shorter. Nick. Up, men. Up, Nick. Nick. There you go. Oh, Nick, you're up. Okay, you froze on me. Okay, sit back down, sit back down. Now I guess I really have to ask this question. Is this better than a video?
Yes.
I mean, seriously, or would you rather just get a video and not have all the interaction? Is this better or worse? I'll do whatever you want.
Much
Much
better.
better.
Okay, I mean, let me know one way or the other. I want to do what's best for you. I know this stuff. I want to make sure you guys get a sense. We could certainly move quicker if I just did a video, but I think the interaction is important.
Would proving this monster be in our next quest?
Probably not. If it was a test, oh yeah. But it's not a test, it's a
Quest.
quest. And I should change the Q to a C and call it quest, okay? My favorite music group is The Roots. Sorry, I love The Roots. That's my favorite music group. And then they're Questlove. But I mean, I should call it Quest. Okay, that's where this stands for freaking COVID. Okay, what COVID's done to my testing ability is what I think of this. When's our first quest? My dad taught me, hit me 3 times. He'll learn. When's our first quest?
Wednesday.
Wednesday. And the question was, would we have to prove this beast? And the answer is no. You're not gonna. Could you have to prove one of these? Could you have to prove one of those? And the answer is yes. Yes. Okay. Okay. Guys, I don't have a lot of motivation for this next result yet, but it's really important, and I'll give you a little bit of motivation. Let's imagine that I've got two vectors in 3-dimensional space. And what it represents really, it represents a truss. It represents a truss that I've got. And what I want to do is I want to come up with a truss system that's going to, I've got these 2 vectors in 3-dimensional space. I want to come up with a support that runs perpendicular from the green vector. I want to run a support that comes up from the green vector, perpendicular to grab this, to carry that load straight down. To carry that load straight down. Does that sound like an important problem? Does that sound like an important problem? Okay, and that's kind of my motivation. I've got these 2 vectors. I'll call this vector B. Now I'm imagining it in the room, but I don't have the room. I only got my board. And I've got another vector A. And what I'd like to do is I'd like to drop a perpendicular down to put a support in here. Now this is where it's going to get odd. I want to rewrite A as this vector plus that vector. I want to rewrite A as the addition of 2 vectors. One vector lies along B, and the other vector lies perpendicular. One vector, you help me out. What did I just say? I know it's been too long. At least talking will help it go. One vector lays. Is it really only going to be Gordon? Can somebody else other than Gordon answer? Come on, help me out, help me out. Dr. Warren, I didn't hear anything you said. Okay, now I'm teaching this guy. What's his name? What's his name?
Yeah.
Jack, listen to me, man. I only care about you. Jack. Yes, Dr. Warren. Jack, I want to decompose A. Say that. Jack, say something.
Decompose.
Oh, good, Jack. Good. Okay, I want to decompose A into a vector sum where one vector lies along B. Say that.
Or one
Or
vector.
one vector lies along.
That's long.
And the other vector lies perpendicular. Now, I'm going to use this symbol. I'm going to call this a parallel. I'm just going to call it a parallel. It runs parallel to B. And then my other vector, I'm going to call a perpendicular. And you're like, Dr. Warren, this is a beast, man. This is a beastly problem. Because it's not in a plane. We have these things running in three-dimensional space. These things are running in three-dimensional space. There's 3 coordinates. They could be at any angle. And you want to find something that's perpendicular. You want to find the segment that runs perpendicular here in three-dimensional space. Now guys, please, does this sound like a fun tool to own? If you could do that, would that be cool? If I gave you two vectors, arbitrary vectors, and said find something that will go directly parallel and directly perpendicular from the green vector to create the blue vector, would that be useful in engineering?
Yes.
Some of you are like, no, I just want class to end, Dr. Warren. Anything, just make it end. This is really cool. And you're like, ah. Now, don't panic. I'm going to put an angle in. What angle did I put in there? Theta. Now, this is the nice thing. Look me right in the eyes. We're not going to need to use theta. Does that make you happy? Okay. But I need to at least theoretically use it. How long is that distance? You're like, damn it, Dr. Warren, there's no numbers. What represents, I hit the ball. What represents how long this is?
The norm of A.
The norm of A. So put that in there. Put that in your drawing. Put that in as the hypotenuse. Put that in the hypotenuse. Write that down. I could write it down and you'd write it down, but you're not learning anything. You write it down. So this is what I'm hoping you wrote down. Who wrote that down? Who wrote that down as the norm of A? Okay, perfect. Now, would this distance be nice to have if we were going to try this game of breaking this apart? Would that distance be nice to have? So you guys are going to help me out. If you have a hypotenuse, H, and you have an angle theta, what represents that distance? If you have a hypotenuse and you have the angle, how long's that support brace? Write it down. Write down what's in your gray matter for it. Because one of them could imagine this could be important next Wednesday. And what do you guys have for me? What do you have for me?
The norm of A times cosine theta.
Okay, yeah, in this case it'd be h cosine theta, but over here it would be the norm of A times the cosine of theta. Does that make sense? How about this distance? Well, I'm not going to use this, but what would that distance be? What would that distance be?
Norm of A sine.
Norm of A sine theta. And guys, you want to be able to do this to build things. Don't fear trade. Embrace it. It's a friend. It's not an enemy. This would be the norm of A times the sine of theta. Okay. And you're like, Dr. Warren, you told me I wasn't going to need theta. You told me I didn't want to need theta. No. We got a buddy over here. We got this last property. We got this last property that we just showed that A dot B. What did we just show using the law of cosines? And again, this is going to help you. What did we just show A dot B was the same as from the law of cosines? The norm of A times the norm of B times cosine theta. Now this is really fun. It's fun for me because I'm a geek. Look over here, guys. Look, you've got A dot B equals the norm of A times the norm of B times the A dot B is equal to the
Norm
norm of A times the norm of B times the cosine theta. Over here, you'd really like to know the norm of A times the cosine of theta. You're like, well, holy hell, Dr. Warren. Look here. Look here, you got the norm of A and the cosine of theta. What could you do with this equality to get the norm of A times the cosine of theta all by itself? What could you do with this?
Divide by norm of B.
Divide by the norm of B. Divide by the norm of B. If I did that, then this length is the same thing as A dot B divided by, help me out, divided by norm of B. Guys, this is so sweet. It's so freaking sweet. This is what we want. It has an angle in it. Is the dot product that damn hard to calculate? No. Is the norm of a vector really that hard to calculate with a calculator? No. And we can get this length without having to deal with the angle at all by using our new friend, the dot product. Okay, Dr. Warren, but we're still a long way. We know this distance is now A dot B divided by the norm of B. It's also the norm of A times the cosine of theta. But this distance is this. I don't want a distance. I want a vector. I want the vector to be A dot B over the norm of B long. You're like, crap, I want a vector and I know I want it to be that long. Well, give me a vector, any vector. Just give me a vector, I'll call it the x vector. Give me a vector.
625.
6, 2, 5. Now, imagine you plotted it. You didn't, but imagine you plotted it. You would go out the x-axis, you go out the x-axis, 6 over the y-axis, 2 and up the z-axis, 5. Now what if I said, oh guys, I really want a vector that's 5 times as long. Points in the exact same direction, but it's 5 units long. Could you figure that out? Could you figure out how to do that? What would you do? If you wanted something that pointed in the same direction as this, but it was 5 units long, what would you do, guys? 5 units long altogether, what would you do? 5 times longer, what would you do?
Multiply the vector x by 5.
Yeah, use your scalar multiplication. Here's a vector that points in the exact same direction. It's just 5 times longer than that vector. This next question's very different. Well, I've got 1 minute. What if I wanted a vector that pointed in the same direction as x, but it was 5 units long? Not 5 times longer. I want a vector that points in the same direction as x. We'll call it C, where the norm of C is 5. That sounds a little more challenging, but it sounds really useful. You're like, well, Dr. Warren, if you could turn this into a unit vector, and then you multiply times 5, would that work? Let me get it back where you can see me. If I turn this into a unit vector first, and then scaled it by 5, would that work? So let's figure out how to do that, and then we're going to end class. Let's turn this into a unit vector. Well, how do you turn something into a unit vector? You take the vector and you divide it by its. You take a vector and you divide it by its norm. So you do x divided by the norm of x. X divided by the norm of x. So that would be the vector 6, 2, 5 divided by the square root. I'll do the math. 36 plus 4 is 40. 36 plus 4 is 40, plus 25 is 65. So this would be a vector that points in the same direction. This would be a vector that points in the same direction as x, but it's 1 unit long. And then if I take this unit vector and multiply it times 5, this would be a vector that points in the same direction as x, but it's 5 units long. Okay, we're out of time. No, what time is class end?
11.
Oh gosh, thank you, thank you. I was like, where did my time go? Oh, hallelujah, hallelujah, okay. So I can keep going. Some of you are like, no, Dr. Warren, class just ended. No, for some of you, your brain shut off a long time ago. I can see your faces. You're smiling at me, but it's like I was. Stuart, how are you doing, man?
Pretty good.
Good. Rhett, how are you doing, Rhett?
I'm doing all right.
Rachel, how are you doing, Rachel?
Good.
Good. Hunter, how are you doing?
Great.
That didn't sound so good, Hunter. Do you have COVID? Okay, good. Just making sure. Greer, how are you doing?
Good, how are you?
Good. Lizzie, how are you doing?
Good.
Mason, you with me?
Yep.
Okay, Dr. Warren, you had time and now you're wasting it. Okay, but back to where we were here. So I'm thinking about what vector would this be? It would be, I'll multiply 5 times 6, 5 times 2, 5 times 5. So the vector would be 30 over the square root of 65, 10 over the square root of 65, and 25 over the square root of 65. This would be the vector that would point in the same direction as x, but it would be 5 units long. It'd be 5. Like, that's one. What are we doing again? Let's take the helicopter up out of Vietnam. Let's look down onto the valley. What we wanted to do was we wanted to decompose A. I'm not listening at all, Dr. Warren. The moment you said decompose, you lost me. I want to decompose A into a vector sum where one part is parallel to B and the other part is perpendicular to B. What represents the length of this vector? This is like an awkward silence on a date. What represents the length of this vector?
Norm of
A
A.
dot B divided by the norm of B.
Yes! Someone like norm of A times the cosine of theta. We're thinking geometrically. It's
A dot B.
A dot B divided by the norm of B. There's the length of that vector. Okay, now I want this vector now. I want that vector. Make it big and bold on your paper. I want freaking A parallel. I want it to go in the same direction as B, but I want it to be that long. Well, let's use what we were doing over here. Let's turn B into a unit vector. So if I was going to do that, like Dr. Warren, there's no freaking numbers like we had over here. It's okay. If I wanted a unit vector that pointed in the same direction as B, what would I do? What would I do? Well, you take the vector B and you divide it by its
Norm.
norm. You take the vector B and you divide it by its norm. Okay, now look at it. Is this really a vector? Honestly, is it a vector? Is a vector divided by a scalar a vector?
Yes.
Yes. This is a vector. U is a vector that points in the same direction as B, but it's 1 unit long. Well, then how could I get a parallel? How could you get a parallel? What was kind of working as that scale 5 that we were doing over there? We wanted a vector that was 5 units long, so we took x, divided by its norm, turned it into a unit vector, and multiplied it times the scalar 5. We want something that's this long. So I'm going to take my unit vector, I'm going to multiply it times that scalar right there. I'm going to take my unit vector and I'm going to multiply it times that scalar right there. So it would be U times the norm of A times the cosine of theta, that would be that vector. But this I don't want to deal with. But this is the same thing as A dot B divided by the norm of B times U, which is the same thing as A dot B divided by the norm of B times B over the norm of B, which is equal to, and this is finally our flashcard, A dot B divided by the norm of B squared times the vector B. And that gives us a parallel. That gives us a parallel. And this, by golly, is a flashcard. That is a flashcard. Now focus with me for a second, guys. It looks miserable. I agree, it looks miserable. The first time I saw it, I almost vomited. I'm like, oh my gosh. That vector is this horrible expression. And then I looked. How hard is it to calculate the dot product of two vectors? I mean, really, computationally, how hard is that?
Not hard.
Not hard. Now look at this. The norm of B has a square root in it, but you're doing what?
Squaring.
Squaring it. So you don't even have a square root to deal with. There's not even a square root. So this is really just A1 times B1 plus A2 times B2 plus A3 times B3 over B1 squared plus B2 squared plus B3 squared. And you multiply that scalar times B, and you're done. So now, I'm going to give you a vector, I'm going to give you two vectors, and you're going to find a parallel. I'm going to give you two vectors, and you're going to find a parallel. Bye, Jack. Okay, my first vector is 1, 2, 3. I'm lazy. My first vector is 1, 2, 3, and B is going to be 4, 6, 2. And what I want you guys to do, maybe here's A, here's B. I want you to find that vector. I want you to find that vector. You find me numerically what represents that vector in three-dimensional space. And your flashcard might help. This flashcard over here might help. Okay, for sake of time, I'll stop you. A vector is an ordered triple of three real numbers. Now, anybody who finished, what was your first real number? What was your first real number? Anyone who finished, did anybody finish? What was your first real number? Maybe I didn't give enough time. Did anybody have a number? Well, then I'll go back and I'll start calculating it. Let me,
88 over 56.
okay, I'm gonna go with this 88 over 56. I'm not sure it's right because I haven't calculated it yet. Did anybody have a second real number? Did anybody have a second real number?
132.
132 over 156.
132 over
56.
56? And then how about your third real number? How about your third real number?
44.
44 over 56. I knew if the denominators weren't the same, we were wrong. Okay, so let's come back here. Let's look at, this is my scalar. This is a scalar, and you're like, Dr. Warren, what do you mean? This is a real number. A dot B is a scalar. The norm of B is a scalar. The norm of B squared is a scalar. This is the vector. So if you're looking at this, it would be the vector 4, 6, 2. Now let's get the scalar here. This would be b1 squared plus b2 squared plus b3 squared. And the numerator is a1 times b1 plus a2 times b2 plus a3 times b3. Let's do the dot product. It's really simple. I mean, even I can do it. It's 1 times 4 plus 2 times 6, that gives me 16, plus 6 more, 2 times 4, 12, 16, plus 6 is 22. So this would be 22. Then b squared is 16 plus 36 plus 4. 16 plus 36 plus 4. And 16 plus 36 is 52, and then plus 4 more is 56. So this would be 22 over 56. And then you're going to multiply this times each of those components. How many people are pretty comfortable with that? How many people think they could maybe do that next Wednesday? How many people think they could really? I'm like, well, Dr. Warren, you've got less than 2 minutes. I hate you, Dr. Warren. Okay. I don't know what to do. I know it's like an hour and 15 minutes. Just look like you're on marijuana. Just look at me like you're on marijuana. Just go ahead. Give me that, because that's what right now I look at my class and it looks like a drug rehab. I mean, I was just looking at it a moment ago. I was looking at my class. I'm like, is this really a drug rehab? Is that what we're doing here? Calc 3, a drug rehab. Sorry, back to where we were here. I wanted to decompose vector A into a vector sum where one part was parallel to B and the other part is perpendicular. And you got, Dr. Warren, you've got 1 minute of my time. I get this vector. It's a little messy, but I get it. How could I get this vector? And then they just went like, okay, now imagine you got this. Here's the vector smiley face. And here's the vector apple. Here's the vector smiley face, and here's the vector apple. How would you get that vector? How would you get the vector that points from here and ends there? What would that vector be? If you got the vector smiley face and the vector apple, what would this vector be? Think geometrically. Think of your vector, your geometry of your vector. It would be the vector apple minus smiley face. So now come back over to here. Do we have the vector A? Are we assuming that we have the vector A? Did you not just calculate the vector A parallel? Did you just not calculate the vector A parallel? And your answer, well, Dr. Warren, I didn't. You did. Somebody else did. How could you find the vector A perpendicular if you know this vector A and you know the vector A parallel? How could you find the vector A perpendicular? Because it's going to end class. You're going to torpedo class like a U-boat, or German U-boat. How could you find A perpendicular if you've already calculated A parallel and they gave you A to start with?
A minus A parallel.
It's just the vector A minus the vector A parallel that you just calculated. I think part of your WebAssign, which is due when? Friday, is to do some of this, is to do some of these things. Okay, you guys are amazing. You guys are amazing. I seriously, you are making it work. You're making this work. I mean, it's hard because we're distant, but the fact you're willing to answer, the fact you're willing to not completely daze out, I love you guys, okay? I mean, you guys are amazing. You guys are amazing. You can learn in anything. If we can learn through COVID, I can't imagine what you guys are gonna build later in life. Okay, I will see you on,
Friday.
get out of my face, Dr. Warren, get out of my face. Okay, I will see you guys. Thank you, thank you.
Thank you.
Thank you. Have a good
Thank
day.
you.
Thank you.
Oh, they're such
Dr. Warren.
Oh, who's there? Cameron, how are you doing?
Good. So my Wi-Fi started messing up, I think because my roommates are also in class. So could you take pictures, like not to, today is fine because I got it from Nick, like Nick will cover me, but could you just keep taking the pictures just in case?
I'm making a
fine.
video, Cameron, that I'll put up also of the lecture.
Okay.
Of the,
Okay.
with the iPad, which is typically a little clearer, so you can just scroll through to the place where you missed, and then you can just pick up with the lecture there.
Alright.
Because
Awesome, thank
I should probably make a video of the Zoom, but I'm just kind of like,
you. No, it
well,
was fine. It worked until like, I don't know, the last 10 minutes it started messing up and kicked me out.
Cameron, I have no idea how you guys are gonna
It's
learn.
fine. It was definitely on my end because nobody else was having problems, so it's okay.
Okay, well, you just keep letting me know. We're just gonna keep
All right.
patching boats, bailing out water. We're just gonna
Yeah.
do our best to get it across the Atlantic, okay?
Good sail.
Get that sail, that's right. So
All
I'll
right,
put up
thank
that
you.
video later today, once it processes it.
Okay. Have a good day.
Oh, you too. I'll go stop the video. Go stop the video. My little videoers, I'm sorry, I forgot to stop you. Bye. Thanks.